Hello everyone, welcome back to Cipher Space Code. In the previous parts of number theory, we learned about modular arithmetic, Euler tolerant function, and concept of order of an element. In this lecture, we will study one of the most important concepts in cryptography, primitive roots, also called a generator. So the main idea is the special element, primitive root, whose powers can generate every element in a multiplicative group. For example, if we work modulo 7, that is set bar 7 set star equals 1, 2, 3, 4, 5, 6. A primitive root can generate all 6 elements through repeated exponentiation. Now let us formally define what is primitive root is. An element G is called a primitive root modulo n if order of G in modulo n equals to phi of n. Phi of n equals the size of multiplicative group. That means the order tells us how many powers of G appears before returning to 1. If order equals to the entire group size, then G reaches every possible element. Thus, the primitive root equals generator. Why it is called generator? Because G raised to 0, G raised to 1, G raised to 2, etc. to G power phi of n minus 1 produce every element of a group. For example, like for modulo 11, phi of 11 equals to 10. Order of 2 in modulo 11 equals 10. Hence 2 is a primitive root. But 3 in modulo 11, its order is 5, which is less than 10. So it is not a primitive root. Let us verify partially that 3 is a primitive modulo 7. So first we have to calculate phi of 7, which is equal to 6. To be primitive, or here we take G equal to 3. So order of 3 in modulo 7 equal to 6 must hold. So we can compute the powers of 3 in modulo 7. 3 raised to 0 is congruent to 1 modulo 7 and 3 raised to 1 congruent to 3, 3 raised to 2 congruent to 2, 3 raised to 3 congruent to 6, 3 raised to 4 congruent to 4, 3 raised to 5 congruent to 5 and 3 raised to 6 congruent to 1. So the generator elements are 1, 3, 2, 6, 4 and 5, which is exactly the entire group. So in conclusion, all elements appeared before returning to 1. Therefore, order of 3 in modulo 7 equals 6. So 3 is a primitive root modulo 7. The sequence of power forms a cyclic pattern called a cyclic group generated by 3. Now let us examine an element that fails to generate the whole group. Text, that is G equal to 2. We can compute the power of G equal to 2 in modulo 7. G raised to 0 equal congruent to 1, G raised to 1 congruent to 2, G raised to 2 congruent to 4 and 2 raised to 3 congruent to 1. Already returned to 1. So the generated elements are 1, 2 and 4. So here 3, 5, 6 are missing. So order of 2 in modulo 7 equals 3. But order of 7 means phi of 7 equal to 6. Hence 3 is not equal to 6. It is not a primitive root. But here the element generated by 2 forms a concept called subgroup. That is 1, 2, 3, 4, which is only a subgroup. Every non-generator generates a proper subgroup of a multiplicative group. So primitive roots are often called generator. So let us understand why. Generator is the set angular bracket G consists of all powers of G. Like angular bracket of G equals set of G power 0, G power 1, G power 2, etc. So there are general case of generators if angular bracket of G is equal to set bar n set star, then G is a generator. Non-generator case, if it contains only some elements, then it is not a generator. For example, we already seen that in modulo 7, 3 is a generator and 2 is a not generator. So A generator allows access to the entire key space. In cyclic group, knowing one generator is enough to describe the entire group. So, the next another important question, do primitive root always exist? No. Primitive root exists only for n equal to 1, 2, 4, p power k, 2p power k, where p is a odd prime. There are some cases. First one is the prime power. Prime numbers, example 7, 11, 13 and 17. The primitive roots always exist. Second case is prime powers. Examples like 9, 27, 125, which are 3 square, 3 cube or 5 square, like. They always have primitive root. Then third case is the twice prime power. Examples 14, 22, 54, like 7 into 2 is 14, 11 into 2 is 22. Like these have also prime root exist. The cases where they do not exist, examples are 8, 12, 15, 16, 20, 24. Prime root doesn't exist for these numbers. For example, for modulo 8, z bar 8z star equals 1, 3, 5, 7. No element has order 4 because 5 of 8 equal to 4. Hence, no primitive root exists. This theorem is one of the most classification result in the elementary number theory. And another question arises is, if the primitive root exists, how many are they? So there is a theorem that states for this, for a prime number p, the number of primitive roots equal to 5 of p minus 1. For example, if p equal to 5, 5 of 4 equals 2. So there are two primitive roots, which are 2 and 3. For 7, 5 of 6 equal to 2. There are also two primitive roots, which are 3 and 5. So for prime p, the number of primitive root is equals to 5 of p minus 1, because the generator corresponding exactly to the numbers relatively prime to a group order. As a prime number become larger, the number of primitive root generally increases. The next is, computing every power can be slow. This slide introduces a faster method, like how to test if g is a primitive root. So the test formula is, for every prime factor q for p minus 1, g raised to p minus 1 by q not congruent to 1 modulo p must hold. This condition must hold. So first step is to find the factor of p minus 1. For example, for p equal to 11, p minus 1 equal to 10. So the factors are 2 and 5. And compute for g equal to 2, we have to compute g raised to 10 by 2 and g raised to 10 by 5. So it becomes 2 raised to 5 modulo 11, which is 10, and 2 raised to 2 modulo 11 equals to 4, which neither equals to 1. So next step is decision. Since all the test passes, 2 is a primitive root. For the failure, like for an example, g equal to 3, 3 raised to 5 is congruent to 1 modulo 11. So the text fails. Hence, 3 is not a primitive root. So this method is used in practical cryptographic software because it is much faster than checking all powers. So the condition is what? We have to find the factors of q of p minus 1. G raised to p minus 1 by g is not congruent to 1 modulo p. So the next slide is talking about why the cryptographer care about this. Because as the primitive root are extremely important, they form a mathematical foundation for many public key cryptographic systems. They create a full cyclic group, which makes groups like discrete logarithmic problems difficult to solve and provides security for protocols such as Diffie-Hellman, ElGamal, and DSA. Without primitive root, this system would fail their strong security properties. Primitive root helps to ensure that keys and cryptographic operation can utilize the entire group instead of small subset of elements. Let's bring together everything learned as well. So we are here, we look the complete example that all elements of modulo 11. Step 1, we have to find phi of 11, which is 10. So the possible orders are 1, 2, 5 and 10, which are the factors of 10. Step 2, check every element, that is primitive root already exists those order equals to 10. So in result 2, 6, 7 and 8 have the order 10. So these are primitive root. But other elements like 1 have order 1, 3 has order 5, 4 has order 5, 5 has order 5, 9 has order 5 and 10 has order 2. So these are not primitive roots. So in conclusion, the primitive root modulo 11 is 2, 6, 7 and 8. So count is 4, which is phi of 10, which matches the theorem. So every primitive root modulo 11 can generate the other primitive root through suitable powers. So let's summarize the complete lecture. That is, primitive root is order of G in modulo n equals to phi of n, which generates the entire multiplicative group. So generator is the another name for the primitive root. It only exists for 1, 2, 4, p raised to p power k and 2p power k. And it have the count only, that is 5 p minus 1 primitive roots exist. For the efficiency test, there is a condition for every prime divisor q of p minus 1 g power p minus 1 by q congruent to not congruent to 1 mod p. Thank you for watching Cipher Space Core.